know before. And I was lucky enough to solve one of the important problems in GR, to know many of my important friends in physics, starting from Hawking, who I did not realize at the time when I talked with him. And then, of course, I have a good luck to meet of his students, Malcolm Perry and several of them. And then I started in the Institute for Advanced Study, where I met Andy Strominger and also Ed Witter. I still remember the meeting that I had with these brilliant physicists, and they really struck me. At the beginning, we didn't have so much in common because I tried the geometry that I did could be useful for physics. They said absolute nonsense. And then so that's good. And then we start out to work on string theory to see the beauty of the subject. At the beginning, I know also nothing about the subject. I insist and listen to them. And I was listening to Coleman Martha when he was a student. I think that I start to learn a little bit more. And then gradually, after sitting in the few years, I gradually understand better. Then, when Coleman has a student called Pesser, and then I had this postdoc called Brian Green. And then Coleman wanted to talk about collinear symmetry. And that was brilliant. And I had difficulty to accept that this is true at the beginning. Because I'm human, I found that Calabi-Yau manifold with negative Euler number is more permanent. There are many more. Hence, the combination prefer negative Euler number. And then, Philip, and then come the extensive calculation, turns out they seem to be symmetric, positive and negative. Without physicists coming in, it would be tough for mathematicians to go on. And among only actually at the beginning was charging on. And then until Miller symmetry came in, and Philip Candelas did the calculation after Pesser and Green. This object, because they solved some problem that mathematicians want to solve for 100 years, never which we did not have the courage to even believe there's a formula that we can calculate. So they calculated it, and they were very successful. We didn't believe it until our friends in algebraic geometry found a mistake in their programming. We have to say that we are wrong, and the physics turns out to be here, because the number they got is true, is good. And then starting on for almost 30 years now, the whole mature and deep subject now is almost running on itself in algebra, and we do not really need physicists to help at the beginning. At one point, then we need them to help. It has been extremely fruitful and important, in fact, for the development of modern physics, representation theory, and now I think into number theory. A lot of interest in number theory. So I encourage our students, young students, to get into this subject, to learn how difficult it is to you when you go to a seminar when you know nothing about. I remember there are many subjects in string theory which absolutely. I insist to sit in the seminars where Coleman runs every Friday. I still remember. But after enough times, I finally got the idea, and then I started to kick, and then it could be helpful. So I think we have to be patient, and we gradually understand each other. And also in the subject of general relativity and many other subjects in physics, mathematics, I think they are extremely interesting for mathematicians. But I feel also physics is difficult nowadays, not like in the old days. You just know a little bit concept, but with no mathematics, you can develop far. But it's not no more that simple. We need to know both. To see tonight, there's this night for physics, which will come. I believe the subject will be evolved not only into theoretical physics, mathematics will soon be important for related to experimental, and I think all these are very fruitful and interesting. So I hope we all come together with no bias against each other. We could complement each other.
Thank you, Dr. Yao. Now let's invite the director of the Institute of High Energy Physics, Professor Yifeng Wang, to the stage to give us his speech. Let's welcome.
Dear distinguished guests, ladies and gentlemen, welcome to the special event of the International Congress of Basic Science in 2024. It's my good news. This is actually the second time we have the opportunity to hold the evening of physics. During the ICBS, which provided us with unique tools, interdisciplinary interactions among the physicists, and the computer scientists. We may also find synergies even within physics. The evening of physics is in particular an opportunity to learn the most about physics, its current development, and its future directions. I'm very that many great figures to attend this event, and so many exciting young faces joining us. A roundtable discussion roundtable discussions with will happen later to address issues have lectured. Historically, gravity was the first forces being discovered and studied. Over several centuries, physicists about it. We all know, even by every middle school students, learn the Newton gravity. And the last century, the development of the general relativity. And in this century, we discovered the graves. So this is actually an ever-moving field, and a lot of new things could happen. Today, we have the opportunity to hear the lectures by Professor Kumar discussing this subject. Professor Kumar Rafa is a Breakthrough Prize and Dirac Prize, and a very famous physicist in this field. And the talk were covering the string theory the quantum gravity. And the title is Quantum Gravity and Predict for Our Universe. So thanks. This is a great event. We are expecting this evening. Thank you.
Now let's invite Professor Karan Vafa from Harvard University to give us his about the quantum gravity and our predictions for our universe. Welcome.
Thank you. Thanks. It's I think my fourth or fifth visit to China, and each time by the hospitality of the Chinese hosts, but now also by this high level of activity. So I'm really impressed by the collection of amazing people here in this conference, and I'm very to be given the opportunity to give a talk here. So I'm going to give a talk about quantum gravity and our universe. So quantum field theories, which describe how the particle interaction works, typically using Feynman diagrams to try this take place, like some of these diagrams in this slide. We basically in many contexts, and in particular in experiments, in high energy experiments like everything seems to be consistent with the pictures we have using quantum field theories. So quantum field theory shape, but the quantum field theories that we typically are good with don't have gravity in them. So things get a little different. Naively, it seems not that different. You just take quantum fields that you have, and you just add Einstein's geometrization of gravity, which means you have the gains that the space and time have some dynamics itself. So you put the whole thing on a curve, dynamical, changing in shape and size and all that. And that seems to be all fine. And I think what is the big problem is this approach does not work. Naively, it should have worked, but it doesn't quite work. In fact, the infinities that appear in Feynman are durable. And so a conventional approach to quantizing gravity does not work. Feynman was the first to discover this, that quantum gravity is in trouble. Naively, the fact that the conventional approach to quantizing gravity does not work might have led one to say, and did not say this, one may have said gravity cannot be coupled to quantum fields consistently and it cannot be dynamical. Of course, that's not true in our universe because we do have a dynamical gravity. It's a different solution. So somehow the fact that quantum mechanics and gravity are naively seem to be inconsistent with the particle physics interpretation of gravity seems to be. So the microscopic world, dominated by quantum world and so on, isn't what we have in Einstein's theory describing things like the scale of galaxy or the universe. So the UV and IR with each other in the context of quantum theory. So what we have learned is a way to solve the context of, which is replacing point particles by strings, vibrating strings, or perhaps multi-dimensional objects. So this has been a solution in the context of string theory to what the problem that Feynman, in particular, the way we think about this in the context of string theory is that we say that the diagrams that should be fattened up to diagrams which involve replacing word lines with word sheets and diagrams describe amplitude with what we call worldsheet diagrams. So things seem to be a function of what we usually do in quantum field theory, just replacing point particle, but by extended. Actually, this is not quite the end of the story, as it turns out. It raises the following question: can we get every consistent quantum field theory in four-dimensional space coupled to a consistent way? In other words, the computation that Feynman was trying to do, does finally or not? Well, so string theory comes with have 6 extra dimensions, and these should be viewed as compact tiny spaces which have thus far avoided detection. And many solutions to what extra compact dimensions can look like exist. Popular class are in fact Calabi-Yama. One of the concrete examples that we have of how we can get potentially viable physics out of string theory. So this is a caricature of that. So at every point in extended space-time, imagine a compact manifold like a Calabi-Yama manifold, which is so small that we cannot detect them with large apparatus we have in experiments today. But of course, what we have will affect what kind of particles we see. So at each point over the space, we have some geometry here. I'm depicting it by a torus. And depending on how degrees of freedom, like strings or membranes, vibrating at a given point in space, we get different kinds of particles. So we have different manifestations of particles that we can get depending on what kind of geometries we pick. So different space, different kinds of observed theories. So one kind of a Calabi-Yama or one kind of manifold gives us with a particular gauge symmetry with a particular number of generations, another one with a different gauge symmetry. The question is whether the right-hand side can become anything you want. Can gauge theory with any matter field, can you order the theory that you like? The left gives rise to it? That is the big question. Indeed, you can get everything on the right. You almost don't need to talk about the left. You just start with the right-hand side. But you don't need to know the details if you're just interested in the infrared physics. Actually, it turns out that, and that is the big theory, is that we cannot get arbitrary quantum field theories on the right-hand side. This is a lesson you set in the context of string theory. I think that's probably, if I were to say what's the most important lesson we learned in string theory, is not only graph framework, but you almost can get no quantum field theories that you like. That the only quantum field theories that you get are special type. In fact, we believe we only get a finite from gravity. That is, in the short distance physics that you end up emerging, you only get so limited that's highly restricted. For example, if you take a maximum trees in what is called n equal to 4 supersymmetric theory, the whole theory is characterized by a choice of a gauge. But in string theory, we always get the rank of this gauge group less than or equal to 20. If you consider a gauge group SUM with m bigger than 23, this is in string theory. So in other words, if you just choose a random group and you say, can this occur? The answer is generically no. Only a finite set of them appear. And not ones over all the possible ones is 0. The measure is 0. So the set of consistent quantum field theories to grab almost non-existence, very small set. That's right. That is, if you just chose a random quantum field theory, it just does not arise from a UV complete theory. So this raises two questions. Does the fact that most quantum field theories do not arise from theory a deficiency of string theory, or a general conclusion about consistent requirements for coupling to gravity? Evidence is emerging that this is not a deficiency of string theory, but subtle reasons for consistency of quantum gravity and connections with basic facts of quantum gravity, such as unitarity and consistency. This has a lot of mathematical ramifications. For example, factifications that we use in string theory are Calabi-Yau manifolds. The number of possibilities would predict that the number of Calabi-Yaus is finite. In this, Yau had conjectured many decades ago from a mathematical perspective. So, and it's still not known if it's true or not. This can only get a finite set of possibilities has this echo in mathematics. Now, what criteria distinguishes a good theory, a quantum field theory, from a bad quantum field theory, which means that you cannot complete it in a consistent theory of quantum gravity? It does not mean that quantum field theory by itself is bad. For example, it's a good quantum field theory by itself. It's a finite theory. It's a conformal theory. So it's a beautiful theory. But the gravity to be part of the mix, you get into trouble for more essentially all gauge groups. To say which ones are allowed, what are the rules of the game? Which kind of theories can you get? How do you distinguish good ones from bad ones? Why is it that we get such a weird thing that typically a lot of that you think are ending up to be bad theories? Part of the reason is that the powerful idea of without gravity is very powerful, is the notion of the effective field theory paradigm. This has tremendously powerful for both quantum field theory, particle physics, and condensed matter physics. The idea that short and long can be decoupled, that you can integrate out the short distance degrees of freedom, come to degree of freedom at large distance. Of course, that fact is true, but there's one more step that is not true. That is, if symmetries are at large distance, you can come up essentially with what the theory can be, some parameters, which in principle can be picked depending on what is the short distance physics. This picture is that if you just give the symmetries and you just say, I want to write down the theory, go and write it down, exists without the complete UV side. And that is where the effective field theory paradigm, so successful, fails. And that is the real lesson we are learning in string theory. So this question is, how do we come up with the right notion of what is consistent, what is allowed? The main issue is what we call the mixing between short distance degrees of freedom and long distance, the infrared degrees of freedom. They mix with each other. Well, how do we measure short distance? How do we come up with short distance? In the context of like in accelerator physics, we take two particles and shoot at each other, and the higher the energy of mass, the shorter distances you can probe. So we take these particles and we shoot them at each other, higher and higher energies, in order to figure out what is going on at shorter and shorter distances. That is accelerator physics. Correct and very powerful. So we go at higher and higher energy. So if you take particles in principle and shoot at each other with higher and higher energies, what is going to happen if you go to extreme high energy? Well, if you go to higher and higher energies, you would think that I'm going to be probing short lengths. That is true until a certain energy. But if you go too high in energy, that paradigm is that when you go to higher and higher energy, instead of probing short distances, you begin to distances, because what happens is that you begin to create a black hole. In other words, when you were the short, suddenly there's this conspiracy that does not allow you to probe shorter than Planck length, and it becomes, instead of getting smaller. So higher and higher energies get related to large distance physics. Large distance become related. That's a piece of physics which is inherently quantum theory with gravity. So units of scale energy 100 units. In other words, the age of the universe itself is a very big number in Planck units. Neutrino mass. The smallest non-zero mass particle we know of, neutrinos, minus 30 Planck units. I'm here rounding off factors of 10 and 100, I'm not careful. The next scale, the scale of particles that we know of, scale and so forth, they're roughly of the scale of GeV and so on, which is about 10 to the minus 20 in Planck units. And then there's another scale which is recently suggested by Large Hadron Collider, in which the Higgs is stable, which is 10 minus 10 in Planck units almost. So there are these, they are related to each other by power laws rather than by factors of constants. Origin of, but some of them they did have. In some form, you can reformulate what you was saying. For example, what is the nature of dark matter? What is the nature? And one of the features of the dark matter is the fact that these are prominent features. Is there any relation between them? That the dark matter is weakly interacting, so small or dependent? From the perspective of particle physics, naively, there is no relation between the small constant in Einstein's equations and particles. The explanation of hierarchy in these strange numbers are among the most important open questions for theoretical physics. Large and small numbers be related to the requirement of consistency of quantum gravity. Actually, no quantum field theory can arise from quantum gravity, or there are very few of them. That means things can be finely tuned, because otherwise they wouldn't exist. The fine tuning might be a requirement for consistency with quantum gravity. The list of possibly consistent theories are so special, this might be not so strange after all. Numbers. In other words, the choice of the compactification of string theory leading to some specific kind end up landing you at a very, very particular corner of what you might think is okay, this big green space here. The ones that can be coupled to gravity is a very small subset of it. They might appear in some very specific corner. It doesn't doesn't have to. And therefore, what appears fine-tuned from the perspective of this bigger space consistency of quantum gravity. So all these mysterious fine-tuning so this is the basic program, is to figure out what are these requirements giving us these quantum field theories that are consistent. Requirements to be consistent, or to be in what we call in the landscape of string theory, that there should be no global symmetries in a quantum theory of gravity. It's amazing the important field for us, important aspect of quantum gravity that does not have any global symmetries. But you might ask why? Why should there be no global symmetries? Is what I would call uniqueness of quantum gravity. Could you have two completely independent quantity? The statement is no. That if you have one consistent theory of energy or finite action processes, that there is no obstruction to go from one to the other. The range of fields in the theory of gravity follows for what we call the duality conjectures in string theory. This force in any consistent theory of gravity against something which is not obvious. This is, and then there are strong restrictions on critical points when you have positive potential. So if you have a potential which is positive, that potential is highly restricted, and what kind of restrictions are you getting? These are related to what's called the de Sitter conjectures. Of some of the things we have learned in string theory in the context of this swampland program. There are just some ones here that I will try to explain to you what is the origin of some of these relatively heuristic fashion. So I will first tell you a story. If you take a fixed charge and a fixed mass, then you get a solution to black hole. You can also have it spin, but let me ignore the spin for now. As the mass of the black hole is bigger than its charge, there is a black hole. In fact, you can even take the mass. That is what is black hole. So the mass of this fat black hole can be bigger than, or you find that there's a requirement for the mass to be bigger than or equal to its charge. Moreover, Bekenstein and Hawking showed that black holes have thermodynamic properties. And combine it with quantum theory, you find that the black hole has entropy, which is proportional to the area of the horizon of the black hole. And the fact that the black holes always evaporate, the only exception being symmetrically decay away. So why aren't there any global symmetries in quantum gravity? Well, what does a global symmetry mean? Global symmetry means something that you would say charge, but no electrical field coming out of it. In other words, global charge, but there's no remnant of it and measure. So why there can't be anything like that in the context of quantum gravity? The electron field, and if you throw that in to the black hole like that, and then the black hole absorbs this charge, but from the outside, there's no difference between the charge inside and not inside, because there's nothing coming out. There's no out. And therefore, it's just an ordinary black hole with a little bigger mass. And then when the black hole of one kind or the other, plus or minus, and therefore, at the end, you find no charge, net charge left over, and no net charge coming out because the evaporation process is symmetric, and therefore you have no conservation of charge. So the global symmetries just evaporate. Why is the unique? We think that there is only one quantum gravity, consistent quantum gravity allowed. Now, this is, you would say, what does that mean, really? Write that on a piece of paper, and somehow it exists, and somebody writes on a different piece of paper, another theory of gravity. The statement is that these two theories, there's a way to go from one to the other with a finite action process. You cannot say that this theory and that theory are two different universes. You can have a process taking one. The context of string theory is that if you take a space and compactify it on some manifold, take the tiny space to be M, and somebody says, I don't like your space, I want a different Calabi. This is no global act. Argue so you can throw black hole and then to this. You are reassuring. So don't live in our universe. There is no option to create. Are we do not have that. There better be charge to be there. To solve any find that black means that according to another black one of charge one of black hole. This is and what is in this high characterizing. Always run into trouble if you take to get if it then you have fields that this tower of states are low. So the ancient fields space. Otherwise, theory. But we believe it and space. Degrees. In fact, there's a potential parameter. Because and if you compute distance, the universe trap us as universe. What should lead to the real world question? Power. One quarter. And you have run or name flying. With this. So is that this is true in all habits. Electric repulsion going like E squared over R squared. That's the usual Coulomb force. And then there's a gravitational attraction, which goes like M stronger electric repulsion than gravitational attraction. In other words, in fundamental units, their mass is much less than their charge. So for example, for the electron, the mass in the fundamental units is about 10 to the minus 23. and the charge is about 10 to the minus 1. Much, much smaller. So in this sense, the gravitational force between electrons is much smaller. The statement is that the quantum gravity reasoning for it. Well, there's a black hole, heuristic black hole explanation of this, which goes like this. Start with an extremal black hole where the charged black hole satisfied charge equals to the mass. And if it's not supersymmetric, we expect this black hole to decay. And if it decays, what's going to happen? Well, you're going to emit elementary charged particle over mass is bigger than or equal to leftover charge. In other words, the Q minus the small q that goes out should be smaller than the big mass minus the small mass that goes out. And if you start with Q equals to m, you learn that the mass is less than or equal to charge. So again, features of black holes suggest a motivation for this weak gravity conjecture, that there are elementary particles whose mass should be less than or equal to their charge. There is further evidence for this weak gravity conjecture. Pure Maxwell theory coupled to Einstein gravity leads to naked singularities in regions with strong E field. In other words, suppose we forget about what I just told you, and somebody says, I want to study Einstein's theory coupled just to a Maxwell theory with no charged particles. Then in certain cases, you find if the electrical field is strong enough, you get naked singularities. Namely, you start with no singularities, and then you evolve the theory, and you suddenly find that there are singularities that are not hidden behind the horizon. There's no proof that this cannot happen in a quantum gravity, but there are principles that suggest that perhaps this doesn't happen. For example, Penrose suggested that many years ago. In fact, without using that, weak gravity conjecture predicts this cannot happen for a different reason. First of all, the fact that pure Einstein theory cannot couple to Maxwell theory without charged particles means that there must be charged particles in this theory. It cannot be a pure Maxwell theory. Secondly, the weak gravity conjecture tells you that not only there are charged particles, their masses cannot be too big, that at least some of these elementary charged particles have mass less than their charge. And then when you take these two facts into account, when you try to find naked singularities in the previous example, you find that these charged particles get created and they screen the electrical field and they get rid of the naked singularity. So from a very completely different kind of motivation, you get solve a different problem. There's another application of the weak gravity conjecture, and that's to our universe. And we are in a situation where there's dark energy, and it's almost constant, at least it looks like it's almost constant, and it's positive. So I talked about the condition that you have an evaporation of the black holes and what restriction it gives you on the mass. It turns out for de Sitter space, you can also consider big black holes. Big black holes that size almost as the size of the whole universe. And in that case, you get an opposite inequality for the mass. In other words, the weak gravity conjecture says that the mass is less than the charge. But if you take a fat black hole in the context of de Sitter, you find that the mass is bigger than the square root of the charge times lambda to the 1/4, where lambda is the dark energy. So if you apply this to our universe, you find that the mass of the electron is between 10 to the minus 1 to 10 to the minus 31 in fundamental units. And the mass of the electron is 10 to the minus 23 in fundamental units. The lower bound mass is basically the mass of neutrino scale. So this is basically telling you that the mass of the electron should lie between the Planck scale, roughly, and the neutrino scale, which is a correct fact of our universe. It is not a very sharp quantitative prediction, but it is a quantitative prediction nevertheless. Moreover, we get restrictions on critical points of theories with potentials which are positive. This is an important question for early cosmology. For example, does inflation really take place in our universe? Can you have a region where you have a flat potential for a long range in field space, where it maybe rolls down to a value of the potential where we have a small value of potential, which we now call the dark energy, perhaps. Now, this is very difficult for us to study in string theory. The tools that we are good at in the string theory context are good when we have supersymmetry or we are at weak coupling. Well, we can ask whether this can be realized at weak coupling. Can we go to regions where we can actually study this? Well, weak coupling, we can study this. In other words, if you go to weak coupling in the language I was telling you about in terms of the fields, means you go far towards the corners of the boundaries of the field space. And then you can study this question, and you find invariably when you study that, you always get exponentially falling potentials. Potentials which are positive exponentially fall down with the field's value, always, with the exponent that you can actually compute. In fact, you find the V always goes like e to the minus some constant times phi for large phi, and the slope in Planck units, V prime over V, is always bigger than or equal to square root of 2, a very specific number. This is actually what you find in all the string examples we can construct. And you can ask, why is this number? Why do we get square root of 2? And okay, so we cannot get something which looks like inflation in asymptotic field regions. But the question is, what happens inside? So far away in field space, you get something which is exponentially falling down, but maybe you can have something like a metastable solution. What is the problem with that? You could have something like metastable or unstable situation depending on where you are. Or you can have maybe like anti-de Sitter space if it's negative. Without doing too much work, we are now seeing that no model of dark energy is stable. That is, if you are, let's say, here, you will at best be metastable. That means you will decay. It might take a long time if the potential barrier is high, but it will decay. So we don't expect to have an absolutely stable positive energy in string theory. Precisely because at the infinities, we always get exponentially falling potentials. And therefore, a positive value will always have a way to tunnel out. So that means you will never have a completely stable positive energy situation. Therefore, without any detailed constructions, we already predict that our universe is going to decay. Whether it's going to decay slowly or abruptly, this doesn't tell you, but it tells you that we should be in a situation where our universe has a finite lifetime. Now, I told you we know quite a bit about what happens for the potential at large distance in field space. But you might be wondering what's going to happen in the interior regions. Can we say anything about in the middle? Could you have a metastable vacuum? What are the properties there? Unfortunately, we don't know as much about there because, by definition, we don't have weak coupling. We don't have a perturbative way to assess them. And we don't have supersymmetric techniques to have a control over these regions. So we are on a limb to try to make predictions from what's going to happen inside. However, there's one idea that has been proposed that will give you a prediction, if it's true, which has the following feature. The proposal is that if you have a situation where you have any kind of potential, it should never be a situation that short distances, smaller than the Planck scale, can get larger than the whole universe. In other words, you shouldn't be in a situation that smallest possible distances that are unphysical, smaller than Planck scale, could overtake the whole universe, become bigger than the whole universe, and exit the horizon. There is no physical proof why this cannot happen. So this is just a conjecture. But if you take this and see what consequence it has, you immediately find that the potentials that you get should fall exponentially with the square root of 2 that I was telling you about. In other words, it predicts that square root of 2 that we are seeing in string theory at infinite distance. It also tells you that if it's true, and if you do have a metastable de Sitter, its lifetime is not too long compared to the Hubble, and you find the bound on the potential age of the universe which is of the order of the 2 trillion years. So this simple picture would propose that you actually not only have a finite lifetime for the universe, but not too far from the Hubble scale. Now, of course, there are a lot of experiments going on these days to measure whether dark energy is changing at all, or what is the story with that. DESI experiment is one particular one which came up with some preliminary results just a few months ago. It's still too preliminary, so we do not know, but it's extremely interesting, as you can see, potentially relating observational physics to some concrete questions that we see in the context of string theory. This also explains the why now problem. Why do we live now at the time where the dark energy has just taken over? In other words, the time scale of the universe is about 1 over square root of lambda, and that's about the age we are now today. Why is that? Whereas the universe could have lived much, much longer if it was a metastable event with a long lifetime. Well, if this says that if you're in a universe whose lifetime cannot be much more than Hubble, then the typical lifetime that you will measure in such a universe is the Hubble scale, like the measurements we have today. So a typical lifetime will be the lifetimes we are measuring. So the measurement of dark energy also signals the end of our universe in a sense. That is, the measurement of the dark energy is a signal that we are in a universe which is about to end. Sorry about that slightly gloomy perspective, but okay. These ideas also lead to trouble with inflation, because inflation typically wants a large region of field space and so forth. There are ways to get around it, so it's not quite a rigorous picture, but there is another feature of the inflation which is at odds with what we are seeing in string theory. We expect whenever you go to extreme parameters, you should get a dual description. One extreme region is going back in time to early universe. If you had a very large temperature, you expect a dual description. You don't expect the same physics taking over, continuing to work. Just like the field space. So temperature is one of them, which behaves like a variable in your theory, and you expect to have a dual description. So it's much more natural to, instead of inflation, to have an emerging universe from a dual description. So now let me just, since I'm running out of time, let me just begin to conclude with the thing that I hinted at, which was the statement that the dark energy is so small, and if you take the distance or the duality conjecture, it actually unifies with the dark matter. So let me remind you what I was saying. I was saying that the dark energy is so small, and therefore the distance conjecture tells you it should be a dark tower. But then, I didn't tell you what is this dark tower. You could ask me, why haven't I seen that dark tower in my universe? What is this? But then you also have another problem. There's dark matter. You ask, what is the dark matter? So you have two problems. One is, what is this tower? The second problem is, what is dark matter? And the problems typically cancel each other out pairwise. And this may be one of those exact situations, that the dark tower that we are talking about is the dark matter. So the natural statement would be that the smallness of dark energy and the existence of dark matter are correlated. And the dark matter being weakly interacting is exactly what we have in the dual descriptions. So we have to have a weakly interacting dark matter, which would be what we expect for the dark energy to be small. So this will predict that the dark matter cannot be directly detected, because it's weakly interacting, because the dual description is gravitationally interacting. And in this, if you put this idea together, you get a beautiful description of the theory where the dark matter abundance seems very naturally linked in such a way that it agrees with what we see in our universe, and it explains the coincidence problem, which is why the dark matter and dark energy, when with the radiation and matter temperature equality happens very close to where the dark energy takes over. And so, in other words, both the dark matter and dark energy get related to existence of a fifth dimension scale of the scale of a micron. Now, in the context of string theory, you might ask, what is this extra dimension scale could look like? This actually is very natural for us in string theory. This is naturally related to a particular kinds of Calabi-Yau manifolds, which was which is has been studied quite a bit in string theory, and in the context of things like Ojava-Witten constructions, where you get an interval connecting descriptions of what's called the heterotic string, E8 cross E8. So you have something which is what would appear in the language of heterotic string as strong coupling, where you have one large extra dimension playing that role. So you would have some story like this, where the extra dimension is like an interval or something like an interval, with our universe to be a 3 plus 1 dimensional slice in it, the dark matter being a gravitons in these 5 dimensions, which is created not because it was there to begin with, but it was because of the afterglow of Big Bang. In other words, the Big Bang, the same thing which created the Big Bang, will also create these gravitons propagating to the 5th dimension. And that gives us the right abundance of the dark matter. It also sheds light, potentially, on the Dirac's puzzle of the scales. In fact, all the scales that we see get pegged to the cosmological constant. You see, in this 5th dimensional gravitational picture, the Planck scale in 5 dimensions turns out to be the lambda to the 1/12th power, which is 10 to the minus 10. The QCD scale gets related to 2/12th power, which is 10 to the minus 20. The neutrino scale gets related to the same scale as the dark matter, as well as the axion mass scale of the QCD, which is about 10 to the minus 13 fundamental units. And the Hubble scale is down to the 1/2, which is 10 to the minus 60. And the dark energy itself, of course, is 10 to the minus 120. So let me conclude. Swampland conditions can lead to potentially observable consequences for particle physics and cosmology. Almost all quantum field theories are in swampland, which lead to a predictive setup, since they are so rare to find good theories. Fine-tuning, such as hierarchy problem, may end up having a totally different solution. We should not be looking for field theory explanations of hierarchy. And that has actually not worked anyhow. And that has been a path that particle physics has taken for many decades now with not much success. Put severe restrictions on consistent quantum theories of gravity. These ideas suggest that there are strong restrictions on light matter, and moreover, the positive energy in the context of quantum gravity leads to instabilities. Distance conjecture, or duality conjecture, suggests a unification of the dark sector, where the dark energy and dark matter are unified into one concept. Namely, small dark energy gives you the light tower, which could be dark matter. And new ideas, such as dualities, are expected to play a key role in early universe. Thank you. Cheers.
Okay, so thank you very much. No questions? Oh, yes.
The answer to that question.
Shimi? Okay.
Okay. Actually, I get very much interested in your duality between the dark matter and the dark energy. But the question is, for dark matter, the pressure is positive or zero. We know that. For dark energy, pressure is negative.
Yes.
So I get confused on how you can dual these two.
Yes. So just to make clear, when I said they are unified, I wasn't saying that there's one object. I said there's one concept that leads to both, namely, the existence of smallness of lambda predicts that there is dark matter. That's what I mean. Not that dark matter is dark energy. No, that's not what I'm saying. Indeed, as you say, dark energy has different properties than dark matter. But the ideas that link them together, connect them to one theoretical framework predicts both.
Okay, I see.
Yes.
Okay, very thanks for the good talk by the professor. So I have a question about the inflation and the string theory. I wondered if the string theory can provide a natural explanation for the inflation, since in a standard mode the scalar field is very real. So, and the Higgs inflation looks not very good candidate.
Yes.
So I wondered if the string theory can provide such a natural origin of the inflating field.
People have tried to construct reasonable models of inflation in string theory, and people are still debating whether they have succeeded. So indeed, it's very difficult to get inflation from string theory. That's at least the fair way to say it. However, the way I think might happen is in the context of string theory, we have learned that a dual description is very natural when you take extreme parameters. So let me think of it this way. Take our universe and think about going backwards in time instead of forwards. What's going to happen? Well, temperature is going to go up, up, up as we go back in time.
Oh, so
let me just continue. So think about temperature in the Euclidean thermal circle. So there's a circle here. When you take the temperature to be large, circle is different size, and then temperature becoming small is a different size. So small temperature, large circle, thermal circle. Large temperature, small circle. So that parameter suggests that there may be a dual description for that physics when you go to dual description. So from all we know in string theory, we expect something else taking over. Okay, that's a natural expectation from string theory. Now, the ideas such as inflation were proposed at a time where we did not know about duality symmetries of string theory. And so we were not even looking for that. We were looking for a unified framework for all fields and one patch of field space to describe everything. Because that seemed like a nice thing. You have a complete description with one Lagrangian. That was the motivation for inflation to describe these. However, in the context of string theory, this is a requirement. You should not have a single patch description of physics. You should expect a dual description. It is a feature, not a bug. We are expecting a dual description. So the answer to your question is that I would expect a dual description, which is not local, relative to our degrees of freedom. So all these issues that inflation is trying to solve, like horizon problem. Why is the temperature here and there are equal? That doesn't sound local. Yes, because the physics is not local of the emergent universe. In other words, what we are emerging from was not local. Our degrees of freedom are not the dominant degrees of freedom back then. We are non-local relative to that period. For example, T-duality or mirror symmetry is an example of it. The degrees of freedom on one universe is not local relative to the other one. So therefore, if the degrees of freedom are reshuffled from the other epoch to our epoch, there would be non-local. And they would be presumably homogeneous. So many of the properties that inflation is trying to solve will be solved in a very different way.
Yes, very thanks.
Cameron, towards the end of your talk, you started talking about a micron size fifth dimension.
Yes.
Does that mean, do I understand that the rest of the Calabi-Yau manifold is also micron size? Does that mean the experimentalists should start looking at new physics at the micron scale?
Well, there are two questions you asked. So first one, the answer to that is that doesn't mean that all directions are Planck scale. In fact, I was assuming that all the rest of them are Planck scale, roughly. So no. But the second question, the answer to your second question is yes, indeed, experimentalists are looking for the micron scale physics. And I happen to be peripherally connected one of these experiments, which is happening in Vienna, to measure the inverse square law potential deviation for the inverse square law for Newton. 1 over r squared force law for shorter distance should become 1 over r cubed if you go sufficiently small, if it's one extra dimension. And so this deviation, strengthening of the Newton's force law at shorter distance of the order of, when you get to a micron scale, is measurable potentially. They have gone up to 30 micron already with no deviation from Newton's law. So we are expecting, we are not too far from observing a deviation, and they are trying to do this experiment, and a time scale is not decades, but within a decade.
Just going back to the inflation, and you said in theory, and it's not preferred for inflation difficulties. The question is how can generate all of the initial conditions, scalar perturbation, especially for the primordial gravity waves.
So that if you're talking
you
about,
have mentioned that not all quantum field theory are consistent. We know that the observed commutative with respect to the Hamiltonian may not be complete. Is it possible to change the situation when we adopt these extra assumptions?
so I'm not sure which question, is this related to the question was asked, or I'm getting confused
Okay,
here.
okay, I can repeat it.
No. There was a question already asked, I didn't answer.
I will go first, Yana. You can.
So there was a question here, which was about the gravity waves, if I remember correctly, and inflation,
Yeah.
initial conditions of
Yeah,
inflation.
inflation.
So, so in this context, so if the thing is emerging,
Emergent,
so you have to have a model of how this emergence works. We wrote a toy model for this based on Witten's topological gravity of how this could happen, for example. That's an idea. In that context, there were no gravity waves, for example. And the spectrum being infrared shift turned out to be related to an anomaly in the topological
So
gravity
this toy
theory.
model may provide us.
Sorry, just a second.
Please.
So therefore, there are ideas to explain the redshift for the spectrum, and it will predict that there is no tensor modes, for example. So these are some ideas that could have concrete predictions.
Yeah. Let me just add one sentence. This means current experiment on the same B mode detection is much more important.
Yes.
Either
you find it or not.
inflation
It's certainly
or
very
rule out
interesting.
inflation.
Yes.
And confirm your
Yes.
theory.
It will be very
Okay.
interesting.
Yeah. Thank you.
Yes.
So I have a question about the dark energy and dark matter duality. So basically, we know dark energy is a constant, and dark matter concentrate in the center of the galaxy. Does this have something to do with the duality, or?
Not per se. I think that is just matter. It's clumps. So that's that. That's all. There's nothing to the duality. The idea that the dark energy and dark matter arise together was related to duality, not where they clump or where they are.
Last question. So, yes.
Yes, you mentioned that so all the quantum gravity are connected together. So I just wonder, for instance, let us take a type 2 superstring on Calabi-Yau threefold. Then you can have different topology transitions, right? Topology changing process. So my question is, how do you, in principle, compute the cost of energy during the process? Whether you can compute that in string theory in principle or not?
Well, you can, in principle, imagine computing the action for going from one Calabi-Yau to another. So that's just you talk about this process and view like Euclidean time, which you just extrapolate from one left corner to an R to the right one. So it gives you a notion of action more precisely than energy, because the notion of energy might not be well posed depending on what exact thing you assume about space-time. So the process, at least the action, should make sense.
But if you have more supersymmetry, then maybe this is flat. Potential is flat, then it doesn't cause any energy. That's it.
It's depending on the context, you may or may not have supersymmetry. Yes. So you could have a situation where you do have supersymmetry. You roll from one Calabi-Yau to another through a G2 manifold or something. It could, in principle, be like that.
Okay, thank you.
Okay, so because of time, so let's stop here. This is really a great lecture. We learned not only many of the theoretical ideas, but also we learned that these theoretical ideas can be tested experimentally, not too far away from now. So this is really a great message, and I hope that the young people taking this message and know that entering this field is not going to have a regret. So it's going to be we are going to have very exciting future. Thank you very much
Thank
to
you.
Professor Wafa. We stop here.
所有好的东西都要经过实验的考验。
To pose problems and to understand, to have a grand view of what is important, not only to solve problems.
Essentially took almost 20 years to solve them.
你可能没有足够多的工具。
You cannot rush it. Experience shows quickly enough does not help. 它有不可预见性，
像追剧一样，可能这样几年就过去。
还有新的很多的问题涌现出来。
一般好的数学都是花好几年功夫才能够成熟的。当时我们开始中心的时候。小猫2、3次，清华书记跟清华校长这个写生同力的这个。
1、2、3，好，不动啊，来这边。
我们要成为一个世界第流的科研交流基地，我们需要产生基础学问，能够对大自然里边出来的问题有深入的了解。你了解一个主要的想法以后啊，它可以分支到很多地方去影响他们。中心成立了15年，我们在科研方面引进了一大批世界一流的学者。
这几年主要关注于微分方程和机器学习的一个交叉。
主要的研究领域是因果推断，包括工具变量。
我的研究领域是拓扑学中的低维拓扑学，
聚焦的是一类从微分几何里来度量的存在性、可计系统以及数论的交叉的联系。
我一开始是做代数表数论，后面我就做一些曲面的一些对称性。
我主要的方向呢是理解这个 ADS-CFT correspondence。
在这种非常 complicated 的 setup 下，你怎么做因果分析？尤其是对于早产儿，有没有一个很大的影响？比如说和医生的交流，比如说和流行病学家的交流，和教育学家的交流。这个是你，比如说1分钟你跳了多少下？基础数学是能够推动应用学科发展非常大的动力。
这2年我们也在探讨用一些机器学习的方法来解一些偏圆方程。传统的偏圆方程的求解方法，我给一个偏圆方程，你去解它1次。如果我这个偏圆方程换了，你要再求解它1次。这一大类解算子，这一大类里面我就不需要再重复的再解它了。你只要告诉我这个偏圆方程，用这个机器学习的方法把你的解给你推到。
The most fascinating forum by the most influential scientists and experts. And they're going to give us their insights about the future of physics study. I'm very excited to welcome the forum guests. They are Professor Alexei Kitov at California Institute of Technology. Welcome. He's the member of the National Academy of Science. Please. Professor Subir Sakhdav at Harvard University. Welcome. He's the member of the National Academy of Sciences, member of the American Academy of Arts and Sciences, Raman Chair of the Indian Academy of Sciences, foreign member of the Royal Society. Professor Karan Vafa at Harvard University. Welcome. He's the member of the National Academy of Sciences, member of the American Academy of Arts and Sciences. Professor Yifang Wang at Institute of High Energy Physics. Welcome. He's the director of the Institute of High Energy Physics of CAS, academician of the Chinese Academy of Sciences, international member of the U.S. National Academy of Sciences, foreign member of the Russian Academy of Sciences, fellow of the World Academy of Sciences. Professor Edward Wheaton at Institute for Advanced Study. Welcome. He's the member of the National Academy of Sciences, member of the American Academy of Arts and Sciences, foreign member of the Royal Society, foreign member of the Academy des Sciences. Professor Ximin Zhang at Institute of High Energy Physics. Welcome. He's the principal investigator of ICBM Popularization Telescope. Professor Anthony Z at the University of California and Santa Barbara. Welcome. He's the member of the American Academy of Arts and Sciences. And now I'm going to deliver the mic to our moderator, Professor Anthony Z.
Good evening. I'm very pleased.
Sorry. Charles Zhang from Soho.com. He's the founder, chairman of the board, and chief executive officer of Soho. Welcome. Sorry.
We should all apologize to Dr. Zhang. I'm very pleased to be moderating this very distinguished group of people. It's extremely panel consisting of, let me read off the names very quickly since they've already been introduced. Alexei Kitaev, Subir Sachdev, Kamran Vafa, Wang Yifang, Edward Witten, and Zhang Xingming, and Charles Zhang, Zhang Chaoyang. I have moderated distinguished panelists before, but I have never moderated a panel that covers such a broad range, because here we have not only distinguished theoretical physicists, which covers several areas of physics, but also one very distinguished experimentalist, and also a giant of industry, entrepreneur, and a pioneer of the internet, the Soho search company in China. So, Mr. Zhang, in order to focus the discussion, given the limited amount of time available, I would like to start by asking two questions to each panelist and have them take turn answering these questions. And then after we go around the panel, I would then open the floor for each one of them to express their opinion about whatever subject they like. So my first question is, we are living in a very exciting but also very uncertain period in the history of physics. So my question is there a comparable period from the history of physics that our present period reminds you of? So I like to, since my last name always make me the last in these kind of panel, so I'd like to start with a reverse alphabetical order this time. Usually it's the alphabetical order. So we will start with Dr. Zhang Chaoyang.
Your question is about the comic time compared in the history.
Yeah, is there comparable?
Comparable.
Comparable compared to our present time. So there's so many young people here thinking about going to physics, but we're in an extraordinary period. Is there a period in the history of physics that reminds you of?
So I've been doing some basic teaching and the physics, basic physics. So in terms of frontiers, I'm not that familiar with. But in the history, I've been studying. I think the most exciting period of time is really in the 1920s, when quantum mechanics was established by Schrödinger, Heisenberg, and all those. So it's really exciting. I don't know whether now it's that kind of probably not, but you guys know better.
Okay, thank you. And from this, we go to Professor Zhang 张新明。
Actually, I'm thinking, I started with, when I was a graduate student, I started a pure so-called particle physics and phenomenology of particle physics. And I gradually moved to the field of astronomy. So I'm major now, the focus is on particle cosmology. But I'm thinking, there are a lot of exciting topics, just like Professor Vafa has already mentioned, and dark energy and dark matter, and also inflation. And all says, all think, for the past 10 years, we are not lucky because we are not discovered the worm dark matter. However, we expect within 5 years, we have a big discovery of dark energies. And currently, I'm working on RCPT, CMB programs. And we also hope to discover the gravitational waves, either confirm or rule out inflations.
Okay, next is Professor Witten.
Well, we know so much more than we ever knew in the past that I find it very hard to compare the present period to any previous period.
But in terms of the uncertainty and the excitement,
well,
especially for young people.
Yeah, well, I mean, there are lots of challenges for young people to tackle. The future is always uncertain, so you can never guarantee to young people just what's going to happen if they go into the field.
Thank you very much. So the next I would like to ask Professor Wang Yifang.
I think it's hard to find something which is exactly similar or comparable. But there's one thing I think could be compared with is particle physics in 50s. I think in 50s, we had a lot of new experimental evidence, and we were wondering what are the right theories to describe them. Now, we have a lot of theories, and we are wondering what kind of experimental evidence can prove one of which is the right one. So it's not the exact same, but kind of similar.
Very good. Thank you very much. And now we come to Professor Vafa. Please.
Yes. I think maybe I can answer the question by allowing myself combining different periods in physics. So I think in some ways reminds me of the time where Newton was developing classical mechanics, where the new mathematics was being introduced to answer physics. In that sense, I think what we are seeing in string theory is somewhat parallel, and we are still developing tools. So in that way, it's similar. And in some ways, also similar to the early days of quantum mechanics, where we are getting pieces of facts that we know is true for quantum gravity in particular. But I would say it's quantum mechanics in slow motion. So take quantum mechanics and slow it down by a factor of, 5 or something, and then that's what's unrolling, I would say, until we get to a principle. We still haven't narrowed down to the thing. Quantum mechanics happens so fast, but we're kind of going slowly in that direction.
There are very fewer people working on quantum mechanics than now working on fundamental physics, right?
Well, there are much more people now, but the facts are much more difficult, I would say, still.
Yes.
To put together into a unified framework.
Yes. Thank you. Professor Sachev?
Okay, I'm usually the last in some when you go alphabetical order, but it turns out in this very unusual pattern, I'm the last, even
because
they go reverse alphabetical order.
Because you're in China.
Yes. Anyway, so yeah, that's a great question. Give me some time to think about it. So I'm thinking back, to the time where, especially at a place like Bell Labs, where principles of solid-state physics were being developed. So I'm a condensed matter physicist, the only one here. Well, I guess Alexei also to some extent. And there were landmark theories like Bloch's law, which led to understanding of the band structure of semiconductors, and the BCS theory of superconductivity. And this had enormous application in understanding really all sorts of materials, and also very remarkable technological applications. So today, I think we are at the stage where we are understanding that due to entanglement and multi-particle interactions, We can have lots and lots of complex phases that were not dreamt of in the early days of solid-state physics. Many of these are found in experiments. And so there's, I think, an exciting period of putting together theory and experiment to come up with a comprehensive picture of different phases of matter. Whether this will have the same technological impact, we don't know, but I think we can hope.
Are you suggesting that young people here should think more about the foundation of quantum physics? That there's a lot of quantum physics we still don't understand?
Sure. I mean, I think I think the principles are there, but there's a lot of emergent phenomena when you take quantum mechanics of many degrees of freedom, and there's certainly many deep questions to be addressed there.
Thank you very much. So now, finally, we come to Alexei Kitaev. My former colleague, I should say.
Actually, I cannot think of a similar period in the history of physics. I can say little about cosmology or particle physics, but for solid-state physics, condensed matter physics, this time is different because people are studying engineered systems. They have more control than was previously possible. They can engineer complex systems, and they can study subtle questions about those systems. I think that hasn't happened before.
No, thank you very much. So my second question is the following. I know we are theoretical physicists, not fortune tellers. So we cannot really predict the future. But since there are so many young people here, I would like you to each answer the question of the following. If we're going to meet here 10 years from now, what will we be discussing? What would be some of the exciting frontiers? And now I'll go in alphabetical order and starting with Alexei Kitaev. 10 years from now.
10 years from now. I hope I hope there will be something exciting that we cannot predict right now. I think that's the most exciting possibility, that something happens that
sorry,
just impossible to predict. And for one exciting thing that is possible to predict is the development of quantum technologies. And I hope in 10 years there will be at least some rudimentary quantum computing capabilities that would allow to simulate systems and answer questions that are currently impossible either with experiment or with ordinary computers.
Thank you very much. You think there will be real advances in quantum computing?
There will be advances. I'm not sure about 10 years from now, maybe 20 years from now.
Very good. Okay, Subir Sakdev.
Okay, well, this is a difficult one. I mean, I guess you can ask, what do I hope will happen?
Right.
Well, I think, I work in superconductivity, and one of the potentially game-changing application of superconductivity is in fusion energy, and that requires better materials. So maybe there'll be progress in much better superconductors. Not necessarily higher TC, but that behave better under strong magnetic fields. So I think definitely there'll be much better materials that are being used in many important applications. I think that one can reasonably hope for that. And then I think also on the theoretical side,
very exciting.
perhaps to that. Hopefully, I would say that if it's my wishful thinking, you heard my talk, so maybe by that time they have discovered the fifth dimension, hopefully, with the right range we have predicted. Let's say the cosmology will say the dark energy is not as constant, or some features of non-constancy in it, maybe getting hints of it. These are, again, some aspects that I alluded to in my talk. But I think, realistically, I think we're going to get a lot of news from cosmology, regardless of whether it's my wish or not. I think that the issues related to other aspects is less clear. For neutrinos, we're probably going to get much more information, much more narrowing down about parameters and all that, which would be interesting for fundamental physics potentially. But I actually think we are heading to a very interesting era for experimental physics results, cosmology or otherwise, actually.
I see. Thank you. That naturally leads into the next speaker, Professor Wang Yifang. So, Kamram seems to think that experimental physics would be exciting in 10 years.
As an experimentalist, I think it's relatively easy for me to answer your question compared to others. Nowadays, all the experiment takes more than 10 years or even 20, 30 years. So we know that we can predict what's going to happen in 10 years from now. So for neutrino physics, I think in 10 years from now, we're going to know the neutrino mass ordering. There are only two options, so we don't know which one is right, but we are going to be sure one of it is going to be known and is going to be the right one. And on top of it, we probably have some idea about the neutrino CP phase. And I think by that time, we're going to talk about neutrino absolute mass. I think there is a chance that we can measure it not in 10 years from now, but probably 20, 30 years from now. But in 10 years, we are going to discuss this problem for sure. And to some kind of reachable level and more interesting level of the mass sensitivity. In high energy physics, by that time we probably have some idea about the results from LHC. We probably get some better measurements, and we are going to have some idea about the future machine, the next collider. So I think we are going to have a better understanding about the Higgs properties, and new machines for better understanding, even better understanding of the Higgs properties will be under planning or probably started the construction.
Oh, thank you. That sounds very exciting indeed. Now, Ed Witten.
Well, I can really only say what I hope we'll be discussing in 10 years. Hopefully, we'll be discussing some kind of breakthrough in understanding the relation of gravity and quantum mechanics, and maybe even some more systematic insight about what string theory really means, what kind of geometry is behind it. And hopefully, in 10 years, we'll be discussing the exciting plans for the next collider. That would be great.
Okay. Thank you. Professor Zhang Xingming.
Because I'm working on the cosmology, and I fully agree with what Professor Wafa said already. And just add one point is, I think dark energy will make a very big progress, but we can confirm dark energy is indeed dynamical. However, you will try to understand to know much more about the dark energy, just like the particle nature of the dark matter needs much more long, because the current data from DAISY only shows 3.9 sigma favoring the dynamical dark energy. And also, the very special is, it gives the equation of state crossover mass 1. This is very hard because 20 years ago, I invented a theory. Until now, after 20 years, and there are a lot of people came out, still very hard to build a consistent theory. However, we know once we try to have a bouncing or emerging universe, we still need this kind of matter, which are called quantum matter. But anyway, this is a very big challenge to the theory. This is on the darker energy. And also within the 10 years, I also hope, because I'm leading an experiment on the RCBT, and currently also, 3 bases, Bar-Cyber array from South Pole and SO, and also RCBT in China, working on the B-mode detections, I hope. And we also forecast within 10 years, we'll give some numbers. And maybe we can discover the primordial gravity waves. Okay.
Thank you very much. And so finally, Dr. Zhang Chaoyang.
So I've been observing, we're at the center stage of the AI revolution. I've been observing the possible impact of the AIGC to our thinking and human mind thinking. So human mind works very differently. We have intuition. Well, the machines, have a repetitive, function of doing things. And, for our intuition, thinking about this very complicated problems, we only consume a few watts. But for a machine to have that kind of intuition, probably have a huge, energy supply, power supply to provide that. So in 10 years, probably AI will probably develop into quite an advanced stage. And probably some of these, the human mind cannot understand, or some kind of the equations cannot be solved, or whether the machine can actually observe some kind of internal linkage or some kind of logic and try to help us to understand, or some computational physics to get some, condensed matter physics, or to have some general, the new materials or new proteins or, new structures that can be actually calculated and, help us to reach that kind of, to see that kind of possibility. That's in 10 years, that's what I'm, observing.
Well, thank you. That sounds also very exciting. Now, I've discovered an experimental fact, just sitting on this stage, that Americans are much more long-winded than Chinese. So we have a lot of time left. I was worried about not having enough time. So all our speakers gave very direct answers and so on. So I actually have time to make up a third question on the spot and ask you guys. Okay, so we'll again go in reverse alphabetical order. Since there's so many young people here this evening, I would like each of you to give a couple of advices to young people. If you were a young person today, what would you be doing? Starting with Dr. Zhang.
You mean if young people to?
You mean to found an internet company, or?
Oh yeah, to start a company. Yeah, I think as a young people, I think the young people really the native of the internet. So I would advise the young people to start some business online.
Okay.
And also in terms of learning physics, I would say there's a balance of knowledge and the creativity. I think you should not wait to to read a pile of books to do some derivation or to do some creative thinking. You should do creative thinking right now. Don't worry about you don't have the knowledge. You just ask questions. Just like the speech by Professor Chu Cheng Tong in the opening speech, that if you don't know any subject, you just sit in those lectures and just sit and listen. And you ask questions, and then you become familiar and become expert on it.
Good, thank you. That's exactly what I like. So, Professor Zhang, advice for young people?
I guess I will still encourage the young people to work on the basic science, especially on the particle and the cosmology.
Yeah. Okay, very good. Ed Witten?
Well, I'm asked this question quite often by young people, and unfortunately I can only give very generic advice, which won't sound very original. Learn all you can when you're young, and be prepared to take advantage of opportunities as they appear, rather than having too much of a preconception of what problem you want to solve.
Very good. That's definitely one way to go. And Professor Wang Yifang, advice for young people?
I think it's very hard to give advice which makes sense. But still, I think physics is a good subject to learn. So I think a lot of people here are actually studying physics. And then on top of it, I still think that particle physics, cosmology, I agree with Professor Zhang that particle physics, cosmology is a very good subject to study and to pursue for your life. There will be great discoveries ahead of us, both in particle physics and cosmology.
Oh, thank you. I'm not sure if Professor Sachdev will agree with everything you said. But, well, we'll come next to Professor Vafa, advice for young people, please.
Well, Khalil Gibran, the poet, has a poem about children.
Iranian poet?
No, Lebanese.
Lebanese poet.
Khalil Gibran. And his poem about children basically says your children are not your children. They are the children of nature, and basically they do not belong to you. They belong to nature. And it's basically the summary of it, I cannot do justice to it, but basically the summary is don't give too much advice. Basically, they belong to the future and we belong to the past. So first of all, the first advice is don't necessarily listen to what I'm going to say. That's the first advice. The second advice is if you really insist, I will say something. But again, modulo the first point. Again, it might sound a bit cliche, and it is, because I think it's a universal truth. Follow your interests, they say. I still believe that's the case. I don't necessarily say you have to do science. I love science. I still love science. Just in answer to your previous question, I said maybe 10 years down the line, the machines might be running the show, and so maybe that might be discouraging to some of the folks here, like, what am I doing here? Maybe in 10 years down the time, they're better. I should say that, in chess, they are much better than us right now. But chess is still a fun game, right? So many people are still playing chess, enjoying it, and so forth. So I think this intellectual activity, regardless of who's the best at it, is fun. Mm-hmm. And I think it's what drives me to do it, because I'm excited about it, not because necessarily I'm better than the machine or whatever. So at any rate, I think follow your interest is my only real advice.
Kamran is a person to my own heart. Physics should be fun. I think that's the most important thing. And in my forthcoming book, there's going to be a photograph of somebody holding a card called Physics is Fun, spelled as P-H-U-N. And in this regard, I should recommend Professor Vafa's book on puzzles that are relevant to the universe. Now, Alexei, but probably ask Alexei to start with a Russian proverb. Huh? Advice for young people, please.
Well, I was going to say the same thing that Professor Waffer already said. Follow your interests, follow your dreams. And another thing is that each person should figure what they're strong at and use that, because different people have different strengths, and if you use your strengths wisely, you can compete better.
Very good. I think this reminds me of something that Hans Bethe, the great physicist, said. Always choose to do something where you have an unfair advantage over the other people. So, again, people are very much to the point, and we have used up as little, very little, oh, I'm sorry.
Well, okay. Actually, Alexei and Kamran have said pretty much what I wanted to say. I guess maybe I'll add one more thing. Of course, do what you enjoy doing most. Don't listen to people around you. And if you're going to be a theorist, that's great. but spend a little time in a lab just to get your orientation on what physics is about.
Oh, that's what I was going to do this fall. I'm on a sabbatical, and I'm going to spend 2 weeks in a lab at Yale, and, just to find out how the other side lives. So we have used up relatively. It's only 7:36. So what I'm going to do now is first open up the discussion to the panelists. So each panelist is now free to say whatever they want, perhaps about any topic they like. And then after maybe 10, 15 minutes of this, we'll open it up to question and answer from the audience. So please. So Subir already took the initiative of saying something.
Maybe I'll ask you a question. I mean, what do you, as an entrepreneur, and what do you want from physicists? What are you looking for when you're
I think
talking to physicists? Or talking to students?
I was trained as a physicist. I had a PhD in experimental physics, and then went to the internet, and then so now I have such a privilege of doing physics purely out of fun, and I don't have any pressure to remember things and to have exams. I don't have any pressure to publish any papers, and I even when I talk to a physicist, when I discuss questions with you or this great physicist, I don't have the pressure of being appear to be stupid or dumb, because I know I'm an amateur. So with this kind of no worry, my mind was just fly, and I think I become so smart. So that's why I really enjoy doing physics now, and that's how So I think maybe this is the trajectory of life. You guys, maybe you want to start a business and make a lot of money, and then come back to do physics sometime in the future in your life.
Okay. Anybody else, please? You don't want me to call upon you.
Physics is really fun. I mean, it's really fun. And
physics should be fun.
Yeah. It's just on the back of an envelope, you do some calculation on order of magnitude, and then you understand everything.
Right.
It's fun.
But you're running a company, I understand. You're hiring
I don't need a lot of sleep, so I work like 12 or 13 hours, so I still find time to do physics.
Does your company like to hire physicists, and why? What is it about physicists you like?
Our company hire all kind of people. So, but I do have a small group of PhD students to work with me on the physics side.
Anybody else? Kamran? Anything to say?
I would only say that since we are having many young people here, that many things and many progress that you might see, review of things sounds overwhelming, because the accumulation of decades and decades of work, and you're just learning maybe some subject and so forth. First of all, you have to be patient. If you find something, it's taking time to sink in, that's perfectly fine. We have been working at it, let's say 40, 50 years, and we are here, so it's not a fair comparison if you feel like something makes maybe sound easier to us because we have had a long time in it. And just be patient, and I think you'll surpass us for sure.
Okay. Anybody else on the panel?
Maybe I can make another point.
Please.
If you look back to achievements by actually even many on this panel, a lot of them have come in different fields of physics or mathematics, have interacted with each other in some unusual way. So another thing I would say that when you're young, especially the students, to have a really broad outlook on everything and just learn all aspects of science just because they're interesting, and you never know when things may come together unexpectedly later in life.
Well, Subir, always speaking my heart. You have a choice as a young person in physics. You can go deep or you can go broad. Either you go with a broad appreciation of physics, or you can go as deep as possible on one narrow topic. So it is a very fundamental choice that you have to make. Okay. Anybody else would like to express an opinion? Yes, please, Professor Wang.
I often hear young people complaining that they were born too late and all discoveries which can be discovered have been discovered already.
Yes.
I had a similar feeling when I was young. But over these 30, 40 years of research on physics, I witnessed a lot of major discoveries in front of me by my friends, my teachers, and so on. So I do see that if you are lucky, if you work hard, you have a chance, at least to witness somebody else make major discoveries. So I think physics is fun. So don't feel you are too late. There were major discoveries in your life.
Well, very good. Anybody else on the panel would like to say something before I open it up to the audience? Okay, maybe let me invite questions from the audience, especially from the young people. But if you have a question that you want to address to a specific person on the panel, please say so. Or you can also address your question to the entire panel. Okay. Nobody? They might have to call on people. Oh, please. Well, maybe somebody else with a very loud voice could ask a question. In the meantime, oh, here.
So I just wanted to add my opinion on this. I'm the wife of Professor Witten, and we have 3 children. And of course, when you have children, you expect them to be exactly like you and to go your way, the same way as all these people here expect you to do something similar to them. There are so many things out there that you can explore. So while I suggest that all of you get a very thorough education in science, there will be other avenues by the time you are looking into the job market, let's say, that we could have not imagined, like neuroscience, biophysics, and AI. This is what our children do. So work hard, learn a lot, but keep your eyes open for all other possibilities out there, not necessarily what the current physicists suggest you.
Thank you. Thank you. Yara also speaks to my heart. In fact, my oldest son, was excellent in high school in physics. And then he went off to Princeton and ended up in Hollywood. And so, anybody else? Please.
Thank you very much. Actually, I have a question for Professor Wang and Professor Zhang. So we know that there are 2 extremes in physics. For example, we go to LHC and so on to higher and higher energies to look for physics beyond standard model. And there is also another extreme, for example, the most precise measurement to look for electron EDM, this kind of thing. Also hope to search for beyond standard model. So do you think these 2 ways are can always be converted or equivalent to each other, or do you think there are things this can do, this cannot do, or vice versa? Thank you very much.
Who are you asking from?
I believe these 2 are complementary. Both are needed. And of course, from personal preference, you may choose one or another. But I think from point of view of physics, they both needed, and we had a lot of examples in the history that both can have can lead to major discoveries. So I think we can pursue, from a point of view of the field, we should pursue both directions.
And Professor Zhang.
Yeah, I guess I agree with Professor Wang said. Just add a few sentences. This is the two sides. One is discovery. You need high energy to discover new particles and the new phenomena or whatever. Second one is precision measurement. Just like, you can have lepton number evaluation or lepton flavor evaluation. Once you can see some signals at low energies, this implies there must be some new particles which mediate this process. So you need to agree with, Professor Wang said.
Anybody else with questions? Oh, please.
Well, I wanted to say something, but it's kind of was just said, but just to say it in my own words, if we would, as I see the relation is that if we're lucky by exploring EDMs, we might conceivably get a clear sign of an energy scale at which there has to be new physics. But to really learn what the new physics is, we'd have to explore it directly with a collider. The indirect measurements would tell us that something is there, but it would be, to really learn what is there, you need to explore it more directly eventually.
Good, please. I'm glad that this question stimulates.
Yes, this is a very good question, actually. So I think the premise of the question is one or the other, which I think as most everybody said here, I think we all think both directions should be pursued. I think that's what science should be. I would add to that in my view, there's not been enough attention to precision measurements. This is not one thing in expense of the other one. We shouldn't say, forget about that, do this, or forget about that, do that. I think there should be more efforts in both directions. And I think the precision measurement type experiments have not been pursued as vigorously as I would have hoped to, given the amount of cost, relatively low costs, and time scale involved. So I think that direction should be explored more than has been done before, not at the expense of going high energy in other experiments either. Both should be pursued.
Very good. I think there was a question here from this young
Dear
man.
Dr. Witten, I'm interested in two questions in the latest journals. One is PNAS 2020 on the undiagnosable pure state, and another is on PRL 2023 about incompleteness for observables in general relativity. I'm curious about your opinions towards these two proofs. Thanks.
Sorry, I'm not sure I'm familiar with the papers you're mentioning.
Okay, one is PNAS 2020 on there exists non-diagnosable pure state on any C-star algebra. And another is incompleteness theorems for observables in general relativity on PRL 2023.
Yeah, unfortunately, I'm not familiar with the papers, so I can't comment.
Okay, I can send it to you.
Thank you.
Yes, there's a question back there.
Hello, I have a question for Zhang Chaoyang. And since you are studying physics and also you open a company and you have a lot of money, and now in the future, like for the future collider, it's very expensive and it's very difficult to get money from the government. So I would like to know if like the industry could support the future collider, or like you can help us.
Well, I don't have that kind of much money, to support a super collider.
But enough money for a theoretical physics institute.
Yes, I do have. I have the money to support theoretical physics research or some kind of institute, because theoretical physics doesn't consume much money at all. Just you need just a great mind and a piece of paper or some computers. Yes.
Well, other question? Oh, please. Just louder. Just speak more loudly. That's.
Sorry. My question is, do we really need higher dimensional spacetime to solve the problem of quantum gravity? What do you think are the shortcomings of the loop quantum gravity compared to string theory?
I've learned to give the following answer, which is that to work successfully in any area of physics, you need to develop the ability to judge for yourself what proposals and ideas are serious and which are not. So I'm not going to share my further opinions.
Thank you.
So, Conram, do you have something to say about this?
The question was about loop quantum gravity and
versus
what?
String theory, I guess.
Sorry?
Is it loop gravity versus string theory? Or? Oh.
Loop quantum gravity is not, I think, at any stage to be comparable to string theory.
Very good.
So that's simple.
There was a question. Oh, please. Question over there.
I have a question to you. What do you think is the balance between science popularization and the systematic study of physics?
Okay. Well, my answer is I'm only a poor moderator. We have to ask one of the panelists. We should address it to the panelists.
Professor Wang Yifang, please ask me. Please answer my question. I'm sorry.
It is hard for me to answer your question, as Professor Xi already deferred your question to me. I actually devoted most of my energy on scientific research, not much on the popular science, nor the books or speeches, etc. So I'm sorry, I didn't do a good balance for you.
Good. Other questions? Please. Oh, right there. Okay.
Thank you. So since this hall is full of PhD students in past, present, and future, then I think this could be a very good topic. So how do you find your very first research topic in your academic life? Thanks. For everyone.
For everyone. Please.
I'm not going to literally answer about my first, because I think it would be more interesting to tell you the genesis of the most interesting paper I wrote as a graduate student. In those days, there were paper preprints. We didn't have the internet. And I literally sat down with a stack of paper preprints several feet high and went through them one at a time until I found a paper that I could see hadn't really been done right and that I could do better. So that was the most interesting paper I wrote as a student.
Anybody else? No? Questions, more questions? Oh, please, the young lady here.
Okay, I have a question for Dr. Zhang Chaoyang. You just said that you are so relaxed to do some physics research since you have low pressures to publish papers, and you hired a group of PhD students to do research with you. So there is a question for you. I want to ask that there is any requirement for your group, those PhD students, for them, do they have the pressures to publish papers or to experience some peer pressures to have a career increasing things like that? Thank you.
So actually, the word I use hiring. Actually, I was not hiring some PhD. I was just working with them, not on research, but on popular science. Actually, try to try to using the live streaming and internet to really to popularize the hard physics, become a so I'm not hiring PhD students.
Okay. So far, most of the questions are from young people. Maybe the not so young people, especially in the front, could ask some questions. If people are shy, maybe I'll call upon them. How about Miriam? Miriam, come on. Miriam would ask a question. No? How about Dongxi, Professor Dongxi, ask a question? Or offer advice to young people? No? Okay, well, if we cannot find any volunteers, or if there are no further questions, maybe we'll bring this session to a close. Thank you very much. I'd like to thank all the panelists. Thank you.